Hello, good evening everyone. I am K. Narsimurthy, presently working as an assistant professor in Government First Aid Women's College, Tumkur. The subject which I am presenting is physics, and this is my 52nd video for the students of Tumkur University of second sem. I have done 51 videos for the second semester students, and I covered the 3 units completely. Means 75% of syllabus I have covered with my 45 videos. And after that, after the 3 units, I have started one new chapter which is transient current, and I finished that small chapter. I finished a very small chapter, transient current, of 5 hours in my 5 videos. Now I am taken up a new chapter, and this chapter is alternating current. I have briefly defined you some of the elementary ideas, elementary definitions of this alternating current. Now we are looking for a very big derivation, that's an Lcr circuit. This is one of the very important derivation for the exam, and it is one complete derivation for one complete question in the first mind. Okay. This is an Lcr circuit in an AC, and I am going to derive an equation for the current here. I am going to derive an equation for current in an AC circuit in a series Lcr circuit, not DC. Where in the first chapter, while discussing the transient current, I derived an equation for the charge in the Lcr circuit, and that was a DC. Okay, but this is an alternating current, source is an alternating source. So I am looking for the current in this Lcr circuit with an AC source. Now we have 3 components: inductor L, capacitor C, and the resistor R are connected in series with an AC source. Let us take VL, VC, and VR be the potential across this inductor, capacitor, and resistor respectively. Right. Now, applied EMF. Applied EMF means the EMF applied by the battery to these circuit elements like inductor, capacitor, and resistor. This EMF is partly used to overcome the back EMF across the inductance, and partly used as a potential drop across the resistor, and rest of the potential is used as to charge the capacitor. Okay. Now the voltage what I am applying is used for 3 things. One is to overcome the back EMF across inductor, one is for the potential drop across resistor, and rest of the thing is to charge the capacitor. Now the method which I am using here to derive an equation for current is the J operator method. In the exam, it is specifically they mention in the question that you should follow the J operator method only. There are some other method. There are 2 more methods to solve this Lcr equation, Lcr circuit in an AC, but that will not be asked for your exam because this is the only thing which is kept in your syllabus. It is clearly mentioned in your syllabus that you have to follow a J operator method to solve this Lcr circuit AC. So that is why you have to follow this steps only. You have to follow this method to solve this particular problem of Lcr using J operator method. Right. So we have a J called operator. This J square, I'll tell you what is this J is. When this J square of this is operated on a vector, the vector will turn 180 degree. The vector will becomes minus A if you operate J square on a vector. If J power 4 operates on a vector, then vector turns 360 degree and it will come back to its same position. So vector A operated by J power 4 will becomes vector A itself. Okay. So you can know that J is root of minus 1. It's an imaginary quantity. J square is minus 1. J cube is minus J. And J power 4 is 1. That is all the details. That is all the informations about the J. J is an operator. Okay, when j square is operated on a vector, it turns to 180 degree. Alright, now we'll move on to the derivation part. Now the equation, the applied EMF equation if I write, so it is used for three parts as I told you. First is across the inductor. Potential across inductor I can write as L into di by dt. I am using small letter for the current, L into di by dt, plus potential across the capacitor. I have been telling you that the potential V across the capacitor is Q by C, because Q is equal to V into C. And the resistor, drop across the resistor is R into I. It is from the Ohm's law. From the Ohm's law, V is equal to IR. So these three are the three potential across the three components of the circuit, and that will be equal to the applied EMF. So applied EMF will be E naught sin omega t. That is what the EMF applied. So I am applying a sinusoidal EMF. This time it is an AC. So sinusoidal EMF I can only write it as E naught sin omega t. It is a sine function with time. Okay. So you all know this omega t is the phase. Right. One important thing is, instead of sin omega t, what I am going to write here onward is an imaginary part of e to the power of j omega t. So sin omega t is nothing but e to the power of j omega t. Students, you understand one thing, e to the power of j omega t is cos omega t plus I sin omega t. So you leave this real part, you take only the imaginary part. So sin omega t can be written as the imaginary part of e to the power of j omega t. So every time I will not write an imaginary part, I just keep on writing e naught e to the power of j omega t. Finally, in the final equation, I will take this as sin omega t. Okay. So till now, till the final equation, I keep on continue writing this as e to the power of j omega t itself. But this is understood that it is an imaginary part of e to the power of j omega t. Right. Now, so equation 1 is written like this. Instead of e naught sin omega t, I have written e naught e to the power of j omega t. Left hand side, I am writing it as it is. Now I know that the current can be written as, it's again a sinusoidal current, it's an AC. So I is equal to I naught sin omega t. Instead of writing sin omega t, what can I write now? I can write this as I naught e to the power of j omega t. Current I can also write like this. So I equals to I naught e to the power of j omega t. Right. If I differentiate this, I'll get di by dt, which is equal to I naught. Coefficient of t, you have to write it here. J omega e to the power of j omega t. It's a simple differentiation. Differentiation of e to the power of ax is a e to the power of ax. Exactly in the same way, differentiation of e to the power of j omega t is j omega e to the power of j omega t. Now, one thing has been done. So I have found the di by dt, which I required to substitute, which I needed to substitute in equation 1. So first term is over. I need to find an equation for Q. I need to find an equation for charge, because second term is Q by C. I need to find an equation for charge. Charge is integral of current. It is writing this in a reverse order. So far I know that the current is dq by dt. Current is the rate of flow of charge. Now I am writing in a reverse way. So current charge is equal to integral of current. Q is equal to integral of I dt. Now I'll substitute current I as I naught e to the power of j omega t. Now it is a very simple thing to integrate. If I integrate this, now you all know that the integration of e to the power of ax is e to the power of ax divided by a. Exactly in the same way, e to the power of j omega t integration will be e to the power of j omega t divided by j omega. That term you have to differentiate in the denominator. Right. Now what I am doing is I am multiplying and dividing the entire equation by j. If I do that, I am not making any difference here. So j will be written in the numerator. Denominator will becomes j square, which is minus 1. I have told you very first itself the value of j square is minus 1. Denominator you will get j square, that I am writing it as minus. Numerator j I am writing it as it is. Now this thing I am writing substituting in that main equation 1. What I am going to substitute? So I am going to substitute di by dt and I am going to substitute q in this equation 1. Look at the equation 1. Equation 1 is L into di by dt. Okay. I will substitute L into di by dt is I naught j omega e to the power of j omega t. And the second term is q by c. Q I can substitute as minus j I naught e to the power of j omega t by omega. That I will substitute. C I will take it as it is. Plus across resistor it is I into R. I know the value of I. I is I naught e to the power of j omega t multiplied by R is equal to E naught e to the power of j omega t. Now what is a common thing here is I can take out this I naught e to the power of j omega t as a common factor in the left hand side. So right hand side also you will find e to the power of j omega t. That cancel with the left hand side e to the power of j omega t. If I have taken I naught, then I will left with here. What I left with? One. It is directly written over there. So if I take I naught, so it is R plus j into omega L minus 1 by omega c. Now if I take I naught in that first equation, the big equation, in the left hand side, if I take I naught as a common factor, it will be R plus j into omega L minus 1 by omega c. If I send it to the right hand side denominator, it will be easily E naught by R plus j into omega L minus 1 by omega c. There is some mistake here. You please correct it. Okay. So this second equation is wrong. You please correct it. Okay. Finally I got an equation 2. That is correct equation. The equation 2 is correct. Okay. Further I will continue with this equation. I naught equals E naught by R plus j into omega L minus 1 by omega c. I have some unique term in the denominator. I will take this term and let me find out what it is. I'll take this 1 by R plus j into omega L minus 1 by omega c. It is a complex quantity. I will simplify this complex number. How do you simplify a complex quantity? By multiplying and dividing by its complex conjugate. What is its complex conjugate? Suppose if it is a plus bi, its complex conjugate would be a minus bi. Exactly R plus j into omega L minus 1 by omega c, its complex conjugate will be R minus j into omega L minus 1 by omega c. Now I am dividing and multiplying by this complex conjugate, that is R minus j into omega L minus 1 by omega c. If I do that, numerator I will get R minus j into omega L minus 1 by omega c. In the denominator I use an identity which is a plus b into a minus b, which is a square minus b square. R square minus j square into omega L minus 1 by omega c whole square. So j square would be minus 1 again. So minus into minus plus. So denominator will be R square plus omega L minus 1 by omega c whole square. Now what do I do is, I write this as R into e to the power of minus j phi. So one doubt arises, can I write this quantity, the quantity which I have taken here, can I write this as R into e to the power of minus j phi? Yes, you can write it like this. So what exactly the R into e to the power of minus j phi is? R cos phi minus R j sin phi. Now this is the quantity. I can write it in that same form. r cos phi minus r j sin phi. R cos phi would be r by r square plus omega L minus 1 by omega c whole square. Minus is there. Okay. Now r sin phi will be omega L minus 1 by omega c divided by r square plus omega L minus 1 by omega c whole square. That is I have written here. Okay. So r sin phi will be this and r cos phi will be this. I'll go back and check. Okay. Right. Okay, fine. This quantity which I have considered, I have simplified this quantity by dividing and multiplying that with a complex conjugate. So I can easily write that quantity as r e to the power of minus j phi, and that is r cos phi minus r j sin phi. And from this I can know that what is r cos phi and what is r sin phi is. Now from this I can find out what is r. R is root of r square plus cos square phi plus r square sin square phi. Okay. So I can write this r like this because it's cos square phi plus sin square phi is 1. If I take out r square as a common factor within the root, you will get cos square phi plus sin square phi, and that is 1. So it is another way of writing an r. That's it. So why I am writing in that way? Because I know the value of r cos phi. I know the value of r sin phi. So that I can substitute there and I will get an equation for r. So now the thing is, now the challenge is to write an equation for r, small letter r, which is a very new quantity, new term which I am introducing here. So once I introduce any new term, I need to write an equation for that. And another quantity which I am introduced here is phi. So phi is also a new term. I need to write an equation for phi as well. So r, small letter r and phi are the new terms which I am introducing in between. So I need to write an equation for small letter r and phi. Now I have written this r as root of r square plus r square cos square phi plus r square sin square phi. I know what is r cos phi is. I know what is r sin phi is. Yeah, substitute and write it here. R cos phi is r divided by r square plus omega L minus 1 by omega c whole square plus r sin phi is omega L minus 1 by omega c divided by r square plus omega L minus 1 by omega c whole square. So yeah, denominator is same. No need to take an LCM. Write the denominator. Okay. It is squaring. In fact, you have to square and write. So denominator will be same. It just simply add the numerator. If I add the numerator, it is r square plus omega L minus 1 by omega c whole square within the root. Now 1 r square plus omega L minus 1 by omega c will cancel with the 1 r square plus omega L minus 1 by omega c in the denominator. Okay. Now I got a very simplified equation for r. Right. R equals 1 by root of r square plus 1 by omega L minus 1 by omega c whole square. So I have written the equation for r. Half of the job is done. Next is I need to write an equation for phi. So I am writing what is r sin phi and what is r cos phi. I have told you already. Now from these two equations I can get phi. Divide one by other, I will get tan phi. If I take the ratio of the right hand side, it will be omega L minus 1 by omega c divided by r. And phi will be tan inverse of omega L minus 1 by omega c divided by r. Okay. Now I have defined clearly what is this small r and what is this phi. Okay. So what I am trying to do from the beginning is I took a quantity which is a complex number 1 by r plus j into omega L minus 1 by omega t. I am trying to solve it. I solved it by multiplying and dividing by its complex conjugate, and I can write it as r e to the power of minus j phi, where I am defining what is r and what is phi. I have clearly defined you what is r is. This is r and this is what the phi. Right. I'll move further. Expression for current, I know it is I equals I naught e to the power of j omega t. I naught is I can write an equation for I have written an equation for I naught in the equation number 2. You go back and check. I have written an equation for I naught in the equation 2. I naught is E naught by R plus J omega L minus 1 by omega C. That thing I am substituting here. Yeah. E naught by R plus J into omega L minus 1 by omega C is what I naught, which is written in the equation 2. Now e to the power of j omega t I am writing as it is. Now what I am doing here is the quantity 1 by R plus J into omega L minus 1 by omega C, which I have solved it, and I have written as R e to the power of minus j phi, and I defined you clearly what is R and what is phi. So I is equal to E naught R e to the power of minus j phi into e to the power of j omega t. Okay. Now E naught, instead of R I am writing it as root of R square plus omega L minus 1 by omega C whole square into e to the power of minus j phi e to the power of j omega t. Now I is equal to E by Z. I am writing this root of R square plus omega L minus 1 by omega C as Z, which is called the impedance, in the AC circuit. And the term here is e to the power of j. I will take out as a common factor omega t minus phi. So this I can be written as I naught e to the power of j into omega t minus phi. Now what I am writing here is I am writing go back to sine of omega t minus phi. So I know it is imaginary part. Imaginary part means it is a sine omega t minus phi itself. So in the beginning it was sine omega t and I have written as e to the power of j omega t. Now at the end I am getting this e to the power of I into omega t minus phi. That I am writing it as sine of omega t minus phi. So lekka barabar. Right. Now this is the equation which I am finally getting. I is equal to I naught sine of omega t minus phi. This is the equation for current in the LCR circuit in the case of AC source. I am getting exactly again a sinusoidal function. It is a sinusoidal wave, but there is a phase. Phi is the phase. Phi is the phase between the current and the voltage. Okay. Now, I have to define these things here after deriving an equation for current. I have already told you Z is the impedance, which can be written as R square plus omega L minus 1 by omega C. Here the impedance is the opposition offered to the flow of current by these three circuit elements: resistor, capacitor and inductor. And I am defining this omega L as XL, which is equal to 2 pi FL. And I am defining this 1 by omega C as XC, which is 1 by omega C. So I can write this tan phi as XL minus XC divided by R. Instead of writing omega L minus 1 by omega C, now I am writing it in terms of XL and XC. Now this phi will be tan inverse of XL minus XC. Now what is actually this XL is the opposition, it is the inductive reactance. XL is the inductive reactance, whereas XC is the capacitive reactance. XL is the opposition offered to the flow of current by the inductor. XC is the opposition offered to the flow of current by the capacitor. So phi is equal to tan inverse of XL minus XC divided by R. Now finally I need to tell you these three different cases. So the first case, if this inductive reactance is greater than the capacitive reactance, if XL is greater than XC, then this phi will be positive. If XL is greater than XC, look at this equation of phi, and phi is clearly positive. If phi is positive, okay, phi is what actually the phase between the current and voltage. Okay, if phi is positive, go back and see this equation. So I is equal to I naught sine omega t minus phi itself, because phi is positive. Now what is, you are getting a minus sign in the current equation, but you are not getting, voltage equation will remain same. I am getting a minus phi in the current equation. So current is lagging. it is very clear that the current is lagging. Current lags the voltage, and that means it is an inductive circuit. If this is the case, if XL is greater than XC, it is an inductive circuit where current lags the voltage, which I mentioned in this diagram. Okay, there is a line where I have shown XL is greater than XC, the current is behind, voltage is the horizontal line. Voltage is always the horizontal line. Now the below line is the current line. Now the current is behind the voltage. Current lags the voltage by an angle phi. The phase difference is phi in the case of XL greater than XC. Look at the second case. In case 2, XL is less than XC. If XL is less than XC, you try to find the sign of phi. Phi is negative. If phi is negative, you look for the I naught. I naught is sin omega t plus some quantity, because phi is negative, minus of minus is plus. So it will be omega t plus some angle. So now we are finding a plus in the current equation. So current will be ahead of this voltage. Current leads the voltage. So that is a capacitive circuit. So current leads the voltage in only in the case of capacitive circuit. So there I have mentioned like this. This is the horizontal line is the voltage, and this line is the current. Current leads the voltage in this kind of, in this situation where it's capacitive circuit, where XL is less than XC. Okay, so phi is positive, phi is negative. Now the current leads the voltage. This is a capacitive circuit. Fine. In third case, if inductive reactance is equal to the capacitive reactance, where now the phi is 0, the phase angle difference between these current and voltage is 0. Now there is no leading and lagging. Current and voltage are in same phase. This is a resistive circuit. Now both are represented by an horizontal line. So current is also horizontal line. Voltage is also an horizontal line. Okay. So these are the very important cases you need to know in these LCR circuit with an AC. Okay. Alright. These three are the very important conditions, and I derived an equation for current in these LCR circuit using J operator method. You need to follow only this method to derive an equation for current in this LCR circuit, because that is mentioned in your syllabus. These are some of the books which I referred. You please go through it. You will understand this derivation better. Thank you.